Welcome to my channel. Today in this session, let us discuss about the design of multiplex. Right? Already we have discussed about the multiplexer, and here we are going to design a multiplexer. So our question is to implement the Boolean function using 4:1 max. It has 4 inputs and 1 input, and the function given us f of a comma b comma c is equal to m, that means a minimal term of 1 comma 3 comma 5 comma 6, right? Initially we need to form the implementation table. Since we have the 4 inputs, the table is provided by d0. I am taking the inputs as d0, d1, d2 and d3, and I'm considering a bar and a, right? And here I have the function from 1, 3, 5 and 6, right? So 1, 3, 5 and 6 is written as 0, 1, 2, 3, 4, 5, 6, 7. Still it has an 8 cases, 0 to 7. Okay. And for implementing this table, whatever the terms given in the function, that means here in the function it is given as 1, 3 and 5. Encircle the terms. Here 1 is given, I am encircling. 5, 3 is given, I have encircled. And similarly 5 is given, I have encircled. And 6 is also given, I have encircled. Okay, whatever the terms given, encircle all those terms. The terms given here is 1, 3, 5, 6. Okay, and coming to the lower cases, the implementation table, check the column D0 column. Here it has the 0 and 4. In the function, the 0 and 4 terms are not given, right? And so we have not encircled the terms. If it is given, automatically we need to encircle, right? Here 0 and 4 is not in the function. I have not encircled. Since the terms are not encircled, I am writing this term as 0, right? If both the terms are encircled, I am writing this as high output. Okay, either one term is encircled and it is in the lower table, lower row of the table, I have considering this as A. And if it is encircled at the upper row of the table, I am considering this as A bar. The gist trick is that you need to check the function, whatever the terms given. So implement the table and then encircle the terms given. If both the terms are not selected, consider this as 0. And if both the terms are encircled, consider this as 1. Either one of the terms is encircled at the lower end of the table, lower row of the table, consider this as A, or at the higher row of the table, consider this as the A, right? This is the logic behind the implementation of the 4 is to 1 multiplexer, right? This is not in the case of the 4 is to 1 multiplexer. It is also in the case of 8 is to 1, 16 is to 1, 32 is to 1, 64 is to 1, etc. Okay, so this is the logic behind the implementation of the multiplex. By after implementing the table, I am drawing the implementing the multiplexer. So 4 is to 1 multiplexer. I have the outputs as 0, 1, A bar. I am drawing this as 0, 1, A bar. And for 0, here this is nothing but D naught. So I am considering D naught. If it is 1 for 1, it is D1. And if it is A, it is D2. A bar, here there is D3. Depending upon the outputs in the implementation table, I am drawing the inputs here. D0, D1, D2, D. So these are the inputs for the 4 is to 1 multiplexer. And for the multiplexer, we need to have and select inputs S1, and S not. I am considering the selecting inputs as S not and N. And in addition to that, there must be also be an enable one. So here this is the enabled one, and this is the function. For the provided function, we have designed the 4 is to 1 multiplexer. I repeat the logic once again. So encircle the terms given in the function in the provided implementation table. If both the terms are selected, we have to provide this as 1. Neither terms are selected, we provide a 0. Any one of the term is selected in the lower row of the table, consider this as a any one of the term is selected in the upper row of the table, consider this is the table. Okay, so this is one kind of the implementation in the for the multiplexer. Here directly the function is given, then the function terms are provided as 3, 5 and 6. In case if the we need, this is the next case. Next case, here there is given us 8 is to, we need to implement the 8 is to 1 multiplication, and the provided function is this. That means a bar b d bar plus ad plus b bar cd plus a bar cd. This is the function, right? For the provided function, we have the 4 inputs. We need to convert this into the four variable type, right? For converting this, multiply with the term and its complement for the provided variable. Here a bar b d bar, the term c is missing, so I am multiplying with c plus c bar. So my terms will be this. I get terms like this. Here these two terms are common, so I am considering as this as the single term. And finally, for I am writing the zeros and ones towards the provided variable type. For this, I am considering 0, 1, 0, 1. We know that this binary equivalent is equal to the decimal value of 6. I am considering this as 6. And for the next term, this is 4. And this is equivalent to 15. And for these two terms, I am considering this as the value 11. And for 0, 0, 1, 1, it is 3. 0, 1, 0, 1, it is 5. 0, 0, 0, 1, this one. So for the provided function, I have made the decimal equivalent value. Minimal terms of terms are 6, 4, 15, 11, 3, 5 and 6. Since it is 8 is to 1 multiplexer and it has the 4 inputs, right? 4 variable inputs. I am considering the implementing the table by 0, D0, D1, D2, D3, D4, D5, D6 and D7. That means 8 is to 1 input. I am considering the 8 inputs. And once again, I am considering the A bar and A here. I am writing the decimal value starting from 0 to 50, right? Since we have the function from 0 to 50. Okay, here for the provided terms, I am encircling. This is the first term provided. For 1, I have encircled here. 3, it is encircled here. 4, 5, 6, 11 and 15. Once again, the same logic. If either terms are selected, consider this as 0. Any one of the term is selected in the upper row of the implementation table, consider this as a bar, or any one of the table is selected as the lower case, consider this as the A. So this is the implementation table for the provided logic function, right? And then we need to implement the 8 is to 1 multiplexer. In the 8 is to 1 multiplexer, I have provided this, okay? And in this, I have a function as f, okay, and also I have the select inputs S0, S1 and S2. I have drawn the select input and also I have provided the enable input, okay. And next we need to provide the inputs. The inputs here are 0, 1, A bar and A, okay. Depending upon the implementation table, here in the implementation table, D naught and D2 are 0, right? D naught and D2 was 0. And D1, D4, D5 and D6 is equivalent to A bar. D3 is equivalent to 1 and D7 is equivalent to A. So this is from the implementation table. Write it once again here. D naught and D2 is equal to 0. D1, D4, D5, D6 is equal to A bar. So D3 is equal to 1. D7 is equal to A. So connect D0 to 0 and D2 to 2. So D0 and D2 is connected to 0. Since we have the implementation table output as such a manner, right? And then, and towards the A bar, here let us draw the A first. A is nothing but is connected to D7. Okay, and A can be inverted by the means of NOT gate, right? So it is inverted by means of this, and it is connected to, here this is A bar, it is connected to D1, right? And it is also connected to D4, and it is connected to D5 and also to D6, right? Okay, and D3 is connected to A. So this is the implementation of 8 is to 1 multiplexer, right? Since for the 4 variable input, we have a 3 select inputs and inputs from D0 to D7, D0 to D7, and D0 to D7 is give is the 8 to 1 in multiplexer. Since it is 8 to 1 multiplexer, we are considering this as D0 to D7, right? And 0 1 A bar, A, this is the output we obtained from the implementation table. Here D0 and D2 are 0, D1, D4, D5, D6 are A bar, D3 is equal to 1, D7 is equal to A, right? So for the obtained output, we have designed the 8 is to 1 multiplexer of the provided input function. In such a manner, you need to design the case. Here, it is generally given as 8 is to 1 multiplexer. If it is an 4 is to 2, 4 is to 1 multiplexer, you need to divide the 8 is to 1 multiplexer by the into 4 is to 1. Okay, if I like this video, like, share and